Hello, my name is Lior Dickstein and I am an AI developer at Sony Semiconductor Israel. I am excited to present our work on data generation for hardware-friendly post-training quantization. This work is a collaboration with my colleagues Ariel Lapid, Arnaud Netzer, and Hi Victor Habi. Post-training quantization, or PTQ, is an essential technique for deploying neural networks on resource-constrained hardware. Post-training algorithms require the user to provide a small representative dataset. However, many applications train models on sensitive or private datasets. Such datasets include security data, medical imaging, facial recognition, or any data bound by privacy regulations. This raises the question, how can quantization be performed on a model without user-provided data? One solution is zero-shot quantization, which eliminates the need for user data by generating synthetic data directly from the information stored in the model. Our work addresses the problem of hardware-friendly zero-shot quantization. In this setting, we aim to quantize all layers of a deep neural network, including the input and output layers, into low-precision formats such as 2-bit or 4-bit without relying on real user data. However, existing data generation methods often produce data that causes significant performance degradation, particularly at lower bit widths. The goal of our work is to develop a data generation method tailored for hardware-friendly quantization. Our approach involves identifying and analyzing the limitations of generated data in fully quantized settings. We then introduce DGH, a novel data generation algorithm that addresses these limitations, enabling zero-shot quantization of models optimized for deployment on resource-constrained hardware. With the motivation of our work now established, let's turn our attention to the analysis of current data generation methods and the limitations they present in fully quantized settings. One significant limitation is a distribution mismatch in deeper layers of the model. Data generation methods typically leverage information stored in batch normalization layers, as the training data statistics are embedded in these layers. Consequently, most optimization relies on batch norm-based objectives. However, these objectives mainly affect the distribution where batch norm layers are present. Deeper layers, particularly the output layer, lack subsequent batch norm layers. This leads to a distribution mismatch between real data and generated data. In this figure, we observe the output distribution mismatch. Model outputs of data generated with a batch norm-based objective are shown in orange, and real data is shown in blue. DGH generated data is shown in green. As we will demonstrate later, DGH effectively addresses this mismatch. Another limitation we identified is the scope of statistics aggregation. While traditional data generation methods optimize on a per image or per batch basis, batch norm layers compute their statistics across the entire set of training data. In this figure, we compare the MSE between batch norm statistics and statistics calculated using real image sets of varying sizes. As expected, the estimation improves with larger sets, while statistics from individual images deviate significantly from the global statistics. These observations highlight the need for a global optimization approach to ensure the generated datasets align with these two desired statistical properties. An additional observation is the impact of data augmentations and image priors on statistics. Batch norm statistics are calculated during the model training phase, which incorporates augmented data. In the figure, we compare the MSE per layer in a ResNet 18 model between the batch norm mean and a mean calculated from an augmented image set, shown in blue, and an unaugmented set, shown in orange. The results clearly demonstrate that incorporating augmentation techniques into the data augmentation pipeline is essential for aligning synthetic data statistics with real data distributions. Furthermore, leveraging prior knowledge of the input domain can significantly enhance the quality and realism of generated images. Considering these limitations, we present DGH, a data generation method specifically designed for hardware-friendly post-training quantization. DGH addresses these challenges effectively. To tackle the distribution mismatch in deeper layers, DGH introduces an output distribution stretching loss, or ODSL. The objective of ODSL is to maximize the output dynamic range, specifically the difference between the maximum and minimum values for each image. To ensure the outputs remain within the model's typical range, we incorporate a constraint per image based on the last batch norm layer. This loss enables the generation of data that fully covers the support of the model's output. Returning to the earlier figure of model output distributions for different image sets, we can see that the distribution of images generated with ODSL align much more closely with the output distribution of real images. Moreover, this loss is versatile and can be applied to various tasks beyond classification. Also keep in mind that ODSL operates on each image independently. Next, DGH addresses the limited aggregation scope. We introduced an aggregation algorithm that jointly optimizes all the images in the generated dataset. Calculating global statistics significantly improves alignment with batch norm statistics. Additionally, optimizing based on statistics calculated across the entire image set enhances image diversity by allowing greater flexibility and reducing constraints on individual images. It is also important to note that this algorithm is scalable and can handle datasets of any size without being constrained by GPU memory limitations. The benefits of global statistics optimization become especially apparent when combined with ODSL, the output distribution stretching loss. As mentioned earlier, DGH's aggregation algorithm allows individual images to deviate more from the global statistics, effectively complementing ODSL, which operates on each image independently. This makes ODSL particularly effective when used with larger aggregation scope. In the figure, we can see the accuracy of a ResNet 18 model on the y-axis with images optimized using different aggregation scopes plotted on the x-axis. The orange line represents images optimized without ODSL, relying only on varying aggregation scopes, while the blue line shows images optimized with ODSL. The dashed line remarks the batch norm size of our GPU, emphasizing the scalability and effectiveness of DGH's aggregation algorithm. Finally, DGH leverages data augmentations and image priors through a pre-processing step added before each optimization iteration. We incorporate data augmentations similar to those used during model training, enhancing alignment with batch norm statistics. Additionally, we ensure the inherent smoothness of natural images without relying on complex loss functions. This step also mitigates a major issue in image generation, checkerboard artifacts, effectively minimizing information loss. To validate the effectiveness of DGH, we present experimental results in hardware-friendly settings where all layers, including the output, are fully quantized to the displayed bit width values. We evaluated DGH on the ImageNet 1K validation set, comparing its performance against state-of-the-art data generation methods and real data. As shown in this table, the results demonstrate that DGH significantly outperforms competing methods, achieving accuracy levels comparable to those obtained with real data. To validate the versatility of DGH, we evaluated its performance on the challenging object detection task using the COCO validation dataset. As shown in this table, DGH consistently outperforms competing methods and achieves mean average precision scores comparable to real data. These results highlight DGH's capability to generate high-quality synthetic data while preserving model performance even for demanding tasks like object detection. In conclusion, DGH addresses critical gaps in existing data generation methods for hardware-friendly post-training quantization. By incorporating innovations such as output distribution stretching loss, global statistics aggregation, and integrating augmentations and image priors in a pre-processing stage, DGH achieves state-of-the-art results in zero-shot quantization. It delivers significant accuracy improvements up to 30% in both object detection and classification tasks, often matching the performance of models quantized with real data. Looking ahead, future research will focus on extending DGH to transformer models to explore its potential in generating high-quality synthetic data for these architectures. This future direction promises to expand the applicability and impact of DGH across a broader range of machine learning tasks. For more details and a comprehensive analysis, we encourage you to check out our paper.